to look at how we can get a change of basis for a vector space. So how can we go from one basis of a vector space to another basis? We've already looked at this in 4.4, where we were going from a basis of a vector space to the standard basis in Rn. But this time we want to completely generalize this and say, okay, how can we go from some basis B for a vector space to some other basis C for the vector space? It doesn't necessarily have to be the standard basis. We're going to start this off by looking at Rn, just because it's the easiest space to look at for this. So if we consider Rn, we know that it already has that standard basis. So Rn, let me cut back, Rn has the standard basis. We call them E1 through En. Okay, so it has a 1 in the ith position, zeros everywhere else. So R3, for instance, the real 3 space has the basis 1, 0, 0, 0, 1, 0, 0, 0, 1. So we know that it already has a standard basis. But if I were to take any n linearly independent vectors in Rn that span the whole space, then they automatically form a basis. So I could also take n linearly independent vectors that span Rn, form another basis. Now, the same goes for any n-dimensional vector space V. So I could always find another basis that I can use. And what I want to know is, how can I go from the coordinates of a vector in one basis to the coordinates of that same vector in another basis? And as I said, we did this before, going from one basis to the standard basis, but I now want to generalize this to two completely different bases. So let's say that we had one basis B that is B1 through Bn. So that is one basis for the n-dimensional vector space V. Okay, and let's take another basis. We'll call it C. Again, it has to have n vectors in it that are linearly independent, that span that whole vector space. We looked at that in the last chapter. So that is another basis for that vector space V. Then there is actually a matrix, exactly as we had before, that will take us from one basis to the other basis. So if we let U be in V, so U is just some vector in that vector space, then I can go from the basis B to the basis C for that vector by doing the following. So I can start out with the coordinates of my vector in terms of the basis B. That will give me one vector. Then I'm going to multiply that vector, that coordinate vector in terms of the basis B. I'm going to multiply that by some matrix. And this is the change of coordinate matrix that goes from B to C. So I end up with the coordinates of that vector in terms of the basis C. So it's the coordinates of the vector with respect to C. Now the question is, what is that matrix? How can we find this matrix? Well, the answer is to go from the basis B to the basis C. So you can see here, we've started out with a vector with respect to our basis B, we've multiplied by that matrix and we've ended up with the coordinates in terms of the basis C. So the way that I go from B to C is by creating this matrix where I write each of my basis vectors in B with respect to the basis C. So I have to write each of my basis vectors in B with respect to the basis vectors in C. And each one of those will form a column of this matrix. So this is the change of coordinate matrix from B to C. So it will change the coordinates of a vector with respect to the basis B to the coordinates of the vector with respect to the basis C. Now the columns are going to be linearly independent, okay? Remember, B1 through Bn, we automatically know are linearly independent because they form a basis. So we know that they are linearly independent. By now writing them in terms of that basis C, all we have done here for each one of our columns is we have performed a linear transformation on each of these BI vectors. So we've performed a linear transformation, and that linear transformation, we've already said, is 1 to 1 and onto, but what it will do is it will then create another set of vectors that are also linearly independent. So we go from one set of linearly independent vectors to another set of linearly independent vectors. So because each of these columns is linearly independent from the others, we know by the invertible matrix theorem that this matrix must be invertible. If the columns of a matrix are linearly independent, it must mean that that matrix is invertible. So this matrix is invertible, as we know its columns are linearly independent. Okay. So because it's invertible, going back to the equation that we had down here, okay, I can rewrite this. And this time what I can do is create a formula where I instead go from that basis C back to the basis B, so I can undo what I've just done. So actually coming back here, if I multiply both sides of this equation through by the inverse of that change of coordinate matrix, what I should get is this formula. Okay, it cancels out on the right hand side because the inverse of a matrix times the original matrix is just the identity. So it cancels out on the right hand side and we get this formula. So what we are actually doing here is by multiplying by this inverse matrix, we are going from a vector in terms of the basis C to a vector in terms of the basis B. So this matrix here is just the change of coordinate matrix that goes from the basis C back to the basis B. So what this tells us is that P C goes to B is just the inverse of the opposite change of coordinate matrix. So if I want to go backwards and go from the basis that I'm in back to the original basis, so I go from C now back to B, it's just the inverse of that matrix. Now this lines up with exactly what we did back in 4.4, where we were looking at going from one basis back to the standard basis. So if you remember, the formula that we had for that was that if I want to get back to the standard basis for a vector x, I multiplied the vector in terms of that basis B, so it's going to be the coordinates of the vector with respect to the basis B, and I'm going to multiply that by this matrix. Now the columns of this matrix were just my basis vectors. So each one of my basis vectors formed a column of that matrix. If you look back in 4.4, we went through and proved this. So this is what I had for that particular change of basis, where I went from the basis B back to the standard basis. This lines up with what I just did, because this matrix should take me from the basis B to the basis E. Okay, we'll call E the standard basis. So in this case, we'll call E is equal to, let me go back on that. E is just E1 through En. Okay, so it's the vectors like 1, 0, 0, 0, 1, 0, 0, 0, 1. So it has a 1 in the ith position, 0 elsewhere. So this time, going back to what I had, okay, I have to write each of my basis vectors in terms of the other basis. Well, in this case, each of my basis vectors in terms of the standard basis is just itself, because B1, we'll just do it for B1, in terms of E is just itself, okay? If you write any vector in terms of the standard basis, it's just itself. So this matrix here is literally each of the columns is just each of the basis vectors, which is PB. So this equation that we had lines up with what we already have from before. So we had, from before, you would technically have that, okay? So it's exactly what we had before, and we've just extended it to generalize it. Now, the question is there an easier way to find this matrix? So we want to know what's the easiest way to find this matrix. Well, as we said, each of its columns is each of the basis vectors in B, so the basis that you're starting out in, it's each of those basis vectors in terms of the basis that you are going to. So I want each of these basis vectors in terms of the other basis. And the question is there an easy way to find this? Well, if we look, just take the ith column. So the ith column of this matrix okay, we're just going to focus on the ith column. So to do that, first of all, I'm going to look at BI, okay? So I want the ith column, so I want the ith basis vector in B, so BI, and I want to write that in terms of the basis C. But when we do this, okay, this is going to be a vector, and remember, when you write a vector in terms of a basis, you want its coordinates in terms of that basis. So I want to write BI in terms of C1 through Cn, and the coefficients of that are what forms my coordinate for BI in terms of C. So if I write this, I'll write it as x1 C1 plus x2 C2 all the way through xn Cn. So I want to write my basis vector BI in terms of my other basis. So it will be some linear combination of C1 through Ci. We know that C is a basis. So taking some linear combination of those Ci's will give me the vector that I want, this BI. So I know that I can write BI as a linear combination of the Ci's, okay? So let's say that BI is this. Well, that means that the coordinates of BI with respect to C are just the coefficients, x1 through xn, okay? So if that is the case, then I know that BI can be rewritten as this matrix. So this is a matrix on the right here, okay? Each of the columns of that matrix is going to be one of my basis vectors in C. So I'm going to have C1, C2, etc. as my columns of that matrix. And then I'm multiplying that by x1 through xn, which are in a vector. So I've got a matrix here multiplied by a vector. This is exactly what we have up here, okay? All I have done is split this up. So it's exactly as we did all the way along when we were doing this early on in chapter 1, where we were taking a matrix times a vector and then writing it in vector form. I'm going backwards on that. I have an equation in vector form and I'm writing that in terms of a matrix times a vector. So I've basically written A times X from its vector form. So these two things are exactly the same, okay? I've just rewritten them differently. So if that is the case, what I effectively have here, call this BI, we're going to call this matrix A for now, and this will be the vector X. So all I have is A times a vector X is equal to some vector BI. All I have here is a matrix equation. And I want to solve for X. I want the coordinates of this vector in terms of the basis C. So I want to solve for X. So what I want to do is to get an augmented matrix. And I want to reduce that down in order to solve for X. Okay? So if that is the case, my augmented matrix is each of my C's on the left-hand side with BI on the right. I reduce that down and I can solve for X. So I can find what the coordinates of BI are with respect to that basis C by reducing this down. Now I have to do this for every single BI. I have to solve this for B1 through Bn, and I have to solve that for every single one of those columns. If you think about it, this is very similar to what we did when we were solving for the inverse of a matrix, okay? I had to solve for multiple columns of the inverse at the same time. So what we actually ended up doing, if I was trying to find the inverse of some matrix A, if you remember, this is kind of off topic, but it's along the same kind of lines. When I had to try and find the inverse of A, I set up A with the identity and I ended up reducing it down to get the identity on the left and A inverse would be on the right because I was trying to solve for multiple columns of A inverse at the same time. I'm going to do the same thing here. I want to solve this with multiple BIs at the same time. So I can solve for multiple sets of coordinates at the same time. So what I'm actually going to do in order to solve that is I'm going to keep my left-hand side the same, but I'm going to solve for all of my BIs at the same time. So by doing this, I am solving for multiple sets of coordinates at the same time. So I can find the coordinates of B1 with respect to C. I can find the coordinates of B2 with respect to C, all the way up to Bn with respect to C. So what I should end up with on my left-hand side, I should end up with the identity. And on the right-hand side, I will have the coordinates of each BI with respect to C. And those columns form my change of coordinate matrix P. So what I want to do is start out with this augmented matrix, okay? You want the basis vectors for the basis that you are going to on the left. And on the right, you want the basis vectors of the basis that you started with. So on the left is the basis that you are going to. On the right, you've got the basis that you started with, okay? You reduce that down, so you reduce using Gauss-Jordan. And you should end up with the identity on the left, and on the right should be a matrix that is your change of coordinate matrix that goes from B to C, okay? If you wanted the change of coordinate matrix that goes from C to B, you would have to swap this augmented matrix around, okay? If you were going from C to B, you would have each of your B eyes on the left and the C eyes on the right, okay? So it's always the coordinates that you are trying to go to always go on the left. The ones where you started out in go on the right. Okay, so let's do a simple example of this. So let's say we're going to let B equal to, I'm just doing this within R2. Okay, and I'm going to have another basis okay, so I have two bases for R2. Okay, if you want to, you can check that they're linearly independent, or you can take my word for it. You have each of these are linearly independent and they span R2, so they're both bases for R2. And what we want to do is find the change of coordinate matrix from B to C. So we're trying to find P such that B goes to C. And find the matrix that goes from C to B. So we also want to find the inverse of that. Okay. Let's start out with the first one. So I want P such that B goes to C is the first matrix that I want. So what I'm effectively trying to find is each of my basis vectors in B in terms of my basis C. So I'm going from B to C. So if I start out with my augmented matrix, because I'm going to C, C goes on the left, B goes on the right. Okay, so I would get my augmented matrix, C1, we'll call it -7, 9, C2 is -5, 7, B1 is 1, -3, and B2 is -2, 4. Okay. Then if you type this into your calculator and do reduced row echelon form of it, you should get, the identity actually ends up on the left, and on the right you get this matrix. Okay. So therefore, this matrix here is my change of coordinate matrix that goes from B to C. So P of B goes to C is 2, -3 over 2, -3, and 5 over 2. Okay. Now, to find the other one, so to find P of C goes to B, so I want to find the change of coordinate matrix that takes me from the coordinates in C to the coordinates in B. Two ways of doing it. Either you could find the inverse of the matrix that we just found. Okay, that's perfectly good way to do it. Or you can reduce the following augmented matrix, where instead, because we are going from C to B, your augmented matrix is now this. So B goes on the left, C goes on the right. And when you reduce this down, you should get the identity on the left and the matrix that you're looking for on the right. It's completely up to you which way that you do this. But either way, what you should find is that this matrix is 5, 3, 6, 4. So if I start out with any vector that is in terms of the coordinates of C, so it's in terms of the basis C, and I multiply by this matrix, I should end up with the coordinates of that vector in terms of the basis B. Okay, so it completely up to you whichever way you want to do it, but either way I would do it on a calculator, whether you find the inverse of it or whether you do the augmented matrix and reduce it down. I would do either way on the calculator, but either way you should still get the same answer. Okay, I would go through the notes online just so that you can read through this again, but you should be, if you want some extra practice, there's a couple of examples that are actually in 4.7 in the textbook if you would like to go through that before I give you some homework problems on it. But the main thing is with this is just get as much practice as you can. Okay, if you have any questions, please let me know, and I will see you in the next video.